thanks for coming back for the second part. So now I will tell you more about the quantum noise in such a sensor and about quantum enhancement possibilities that will allow us to improve the sensitivity of the sensor. Okay, so again, because it's a quantum sensor, we are somehow affected by the quantum mechanics, and in this case, mostly by the uncertainty relation. And this is affecting all kind of sensors, starting with like interferometers, like for the gravitational wave detectors, with atomic clocks and with atomic magnetometers. And I would like to tell you a bit about the origins of quantum sensing ideas. So these are the topics that people are thinking for quite some time now about. And I would like to start with Vladimir Braginsky. So he was the first to propose the quantum enhancement of sensitivity. So what he did, he noted that when you have an oscillator and you continuously monitor the oscillator, then the measurement back action is like continuously fed into that oscillator. And this affects you. This affects in the end your sensitivity. So you have this measurement back action. You measure X and that perturbs P, but then the perturbed P affects X. And this is the measurement back action. And this is happening because X and P are bounded together by the uncertainty relation. So whatever system we have, if we have a measurement back action there, we will be bounded by that. If we are observing something and then it's bounded with another observable by the uncertainty relation, then we will have a problem with this measurement back action that will be happening there. And each time we will reduce the noise in one component, we will have to pay the price of that in increasing the noise in another component, right? So also what he did, he noticed that, he marked that this leads to a standard quantum limit. So this measurement back action that I will be telling you more about in a moment, together with another kinds of quantum noises that are in your system, they define the standard quantum limit that your sensor will be operating at. So again, what he noticed, what he was observing was this oscillator. So initially, like we didn't do any measurement. We have a big uncertainty both in the P and an X, in the momentum and in the position. And then we measure X, and this increases a bit the uncertainty in the P, and we precisely know the X. But then it's an oscillator, so we rotate. And then what he did, he actually noticed that in contrast to this continuous observation of the oscillator, if you measure it stroboscopically, if you measure it twice per cycle, then the disturbance that you put into the momentum, into the P, it has oscillated and it became the disturbance of minus P. So again, it's not affecting X. So if you measure your oscillator twice per cycle, you can actually create kind of a squeezed state there, and you can have a very good precision of reading your one component like X at the cost of increasing the noise in the other you can disturb P in this case, but this does not affect your X readout. And in that way, you can get the sensitivity that is beyond the standard quantum limit. So he noted that by observing this oscillator twice per cycle, you can increase the sensitivity of your detection. You can operate below the standard quantum limit. And this is something that is called this measurement back action evading measurement. So by using this stroboscopic measurement, by creating this squeezed state of the oscillator, you can mitigate the measurement back action. And you can have the detection with the uncertainty that is better, with the sensitivity that is better than it would be when we talk about the standard quantum limit.
But I mean, you can also measure it once per cycle.
You can also measure it once per cycle, yes, of course. Or once per 2 cycles, yes. Okay. And then what he also did, he introduces the concept of the quantum enhancement with that. So with using techniques that can help us to improve the sensor performance. So either it can be this stroboscopic probing, or we could use some other kind of enhancement, like using squeezed states of light, spin squeezed states. And my talk today will be more about using squeezed light to get this quantum enhancement. Yes? Yes?
So on the last slide, you showed us those graphs with the phase space. And to me, it looks like going from the first graph to the second one, you squeeze the light, you get narrower in the X and you get wider in P. And then you say you can squeeze it again, you can measure again, and then you can, I guess, get to the second last one where it is narrower in both X and P than it was in the original one. And I'm wondering why that doesn't violate Heisenberg's uncertainty.
It's kind of reaching Heisenberg limit. It's the standard quantum limit is the upper bound in this sense. So the it's not crossing Heisenberg limit.
Okay, so
it's so big because here you didn't measure anything the first, and then you start measuring. So you started creating this squeezed state by measuring properly, like stroboscopically. That's why this uncertainty goes down.
Thank you.
And then actually another proof that this is happening, I found in the Museum de Ciencias Naturales de Barcelona. I went there for a trip and I found this penguin. It's a part of the evolution exhibition. And then the first sentence here is, one of the things that can disturb us most is uncertainty. And I think it's very beautiful because that in case is very, very true when we talk about quantum sensors, that we have to pay the price because of the uncertainty principle. So again, we measure X, it perturbs P, but this perturbed P perturbs X, and this is the measurement back action. Okay, so now with this background, the first efforts to somehow use this idea of the stroboscopic observation of an oscillator was applied in the magnetometry, in those two papers from Romali's group by Yorgos Vasilakis. When they exactly applied this, they were probing, they spin ensemble once per cycle, they polarize it, then it was processing in the magnetic field, and they performed this stroboscopic probing. And then here you can see they were scanning the frequency of this probing, and then at the resonant frequency, they noticed that the noise was decreased with respect to the noise they have seen for the unpolarized ensemble. So they started seeing signal with the noise lower than should be because of the standard quantum limit. Okay, so so it is like analogous to what Braginski has proposed. And then, the story does not end here. We can also think now of spins as spins and not as a harmonic oscillator. So harmonic oscillator has X and P, but for the spin, we have 3 components. And this is actually even better than what Braginski has proposed, because now we have more possibility, right? Because now we could measure Fx and Fy, why we could put all the perturbation, all the uncertainty into the Z component, let's say. This means that we could try to treat it like a harmonic oscillator, in a sense that we could try to measure the amplitude and the phase and not be affected by the increased noise, because we can try to shunt all the noise that we're gonna get because of the measurement back action to the unmeasured spin component. And this was done in those papers with cold atoms and with hot vapors. And I'm gonna be talking about this approach. This was introducing quantum enhancement and evading this measurement back action by pushing all the additional noise into the unmeasured spin component. Okay, so this is kind of an introduction.
Was it also from your group?
Sorry? So this was done by Hara Truliniu in Morgan's group, yes. So I will be talking about those 2 papers. Okay, but going a little bit back to the introduction, I maybe would like to tell you something about quantum enhancement first, and maybe we could use for that the gravitational wave detectors, because I think this is by far the most known use case of applying squeezed light to get a better readout. So what they are trying to do, they are trying to have a super huge interferometer of a very long arms. And then what they are trying to detect is the difference in the path when the gravitational wave is there. They are trying to to really find a very, very, very tiny perturbance of that system. And they need an extremely high sensitivity. And this is happening in many places, not only the LIGO that you may have known, there are more interferometers like that. And I told you before that cold atoms require a lab and all the ultra high vacuum, but this is nothing compared to this kind of collaborations when you have a lot of authors that are trying to really, really measure one thing. And again, this is some sort of a sensor, right? They have this interferometer, and what they are interested in is to have this sensitivity very, very high so that they can really see the perturbance that comes from this gravitational wave. And what they have to do first, they have to measure the sensitivity, and they have to figure out what kind of noises they have in the system. And they have a lot of noise sources. This maybe is even better. They have a different contributions that are coming from different reasons. And one of the noise they have in their system that was limiting their detection was a shot noise. So what they were trying to do, they were trying to, maybe we can see it even better here. Here at higher frequencies, they have this noise that is coming from the photons itself. So they use, of course, the the laser beam to detect, to see the response of the interferometer, and the shot noise that comes from the photons was limiting their detection. So they were trying to beat this shot noise. So let's talk about the shot noise in the interferometer. Interferometer, we have this Michelson interferometer, we have two arms, and then what is happening there is, maybe this one is better. What we have there, we have the ports of the interferometer that the vacuum comes in. And this vacuum is having some sort of a noise, right? And then what was done as the beginning of thinking of the quantum enhancement in these interferometers was done by Caves in 1981. What he proposed is to use parametric amplification. So we have some medium, we can have this medium pumped with some pump beam, and this can create a squeezed vacuum because of this nonlinear response of this medium. And then what we can get is a squeezed vacuum. What you can see here is a squeezed and anti-squeezed vacuum. So what is important here, that we have techniques that can suppress the noise in the light or can increase that noise in the light because of this process that is happening in some sort of a medium. So what they did, they built a squeezer, and now maybe I will tell you a few words about how we can generate this squeezed light, because this is effectively what I will use in the magnetometer. Yes?
Microphones.
Maybe can you please specify what is the vacuum noise?
So
or where is it coming from? Because if you have a vacuum, there's nothing inside.
these are like random fluctuations. So eventually what you have, you detect the photons on the detector, and they will have some discrete detection on the detector, right? So these are, so the question is, what is a shot noise?
No, where comes the vacuum noise?
Morgan, I need to move you a bit. Okay, so we have a laser that goes here, right? And then is reflected, and then it goes to detection, and we have the second part that is reflected here, right? So this is like an empty port, right? But there is a vacuum coming through that port, which is like a noise, right? Morgan, do you have a better way of explaining that?
So the question is, what is vacuum noise, I guess?
You're unmuted.
Yeah, if I understood the question, it was what is this noise of? This is noise of the electromagnetic field. So if you had, in principle, if you had an antenna that was fast enough to see optical fluctuations, then you would see this even in the absence of any photons of any light. And we don't really have antennas which are that fast, but those fluctuations are really there, and they will interfere against a laser. And when they interfere against a laser, then it gives you a noise which you see on a detector. So what the detector sees I think as illustrated in this bottom circle here is the contribution from the laser, which might be very clean, plus the contribution from the vacuum fluctuations, which in this picture have been squeezed. And so, does that answer the question?
It took his microphone away, but he nodded.
Okay.
Again, sorry.
Okay, I was told that that answered the question, so I mute myself.
Yes.
When we say squeeze the vacuum, so at each instant of time, you have squeezing along one of the quadratures, but you continuously change between P and X. How does it work? Okay.
Here, yes. So this will be, okay, let's stay here for a moment. Yes, that's true. So you squeeze one quadrature and you anti-squeeze the second. It can be amplitude versus phase. It can be a polarization of the light. So what we do, for example, is a polarization squeezed light. And that, as it's here, so we look at this phase, the relative phase between this squeezed vacuum and between the light, because we do like a, I think it's called bright squeezed state. So we have a local oscillator and we have a squeezed vacuum. And then we can, what we want to do, we want to match this phase. And based on how we match the phase, we have either squeezed light or anti-squeezed light. And how it happens in the actual experiment is that we have some sort of optical, in this case, system that can generate the squeezed light. And for our case, we have master laser that is resonant with rubidium. It's 795 because we work with rubidium 87. And then this serves as a local oscillator, but it also pumps a nonlinear crystal to create a blue light to do the frequency doubling that later on pumps this nonlinear medium to create the squeezed vacuum. So in this case, I'm getting my squeezed vacuum and I'm getting my local oscillator. And then what I want to do to see this, what you were asking about, I want to scan the relative phase between the local oscillator and the squeezed vacuum. And I can do it on many ways. In our case, what we have a piezo mounted on a mirror of a local oscillator, and we just slowly scan the phase of the local oscillator.
So if you have the pure squeeze vacuum, it's basically like an ellipse in px state that rotates, and then you lock the phase, so you see the fixed one. Okay.
That's actually an excellent question, how to lock the phase so that it stays squeezed or not squeezed. So how we do it, we do something we call the noise lock. So we look at the noise level at the balance detector, and I know the level of the coherent light, or the shot noise of the coherent light, and then I start operating with the piezo. I start scanning the phase, and I can see that sometimes my noise is lower than that, sometimes my noise is higher than that. And with the balance detector response, I try to lock the phase so that it's either squeezed or anti-squeezed. And then that's what I would be using to probe my atoms with in the experiment.
Thank you.
Okay, so if there is anything I didn't say here. So yes, so we have this main laser, we pump the crystal, we create a squeezed vacuum here in the cavity. This cavity is resonant with 795, and then we merge the squeezed vacuum of one polarization on the PBS cube with the local oscillator of the same laser of the orthogonal polarization. So what we create here is a polarization squeezed light. And then this polarization squeezed light goes to a detection scheme. So as for the magnetometry, we have a balance detector, we have a polarimeter, we have a PBS cube before and a half-wave plate or a Wollaston, or we just have a Wollaston prism, doesn't matter. We use both, and then we look at the shot noise on the detector. Okay, and this can go either to an oscilloscope or to a spectrum analyzer. So what we see when we do that on the spectrum analyzer, first we send here just the coherent light. To send here just the coherent light, I just cover this. I cover the pump. I'm not pumping. I'm not creating any squeezed vacuum. So I don't have this interference here between squeezed or anti-squeezed vacuum with my local oscillator. I just have a coherent light. That's how I know I have just a coherent light, because this is blocked. And then I can observe either on the oscilloscope some signal of a given variance, right? Or I can observe it directly on the spectrum analyzer. So I observe the noise level of my light, the photon shot noise it's called, on the spectrum analyzer, and then I compare it with when I pump. I start pumping the nonlinear crystal, I start creating a squeezed vacuum, and I start creating a squeezed light. And it's a polarization squeezed light, so this detection can have either higher or lower noise. And what I do, I scan it very slowly, so I change the phase by scanning the piezo, and you can see that the noise goes way below, 2 dB below the coherent light photon shot noise level, or it goes up. And you can probably notice also that it's not symmetric. I don't get same amount of squeezing and I get anti-squeezing. This is because of different impurities in the system and not perfect optical elements and all the losses that are happening there. I'm losing a bit of squeezing. That's why I can only observe this. Also, the efficiency of the detector itself will not allow me to detect all the squeezed light I could detect. That's why it's not symmetrical. So we see this, and this is how it looks on the oscilloscope, right? So I see either less or more noise, and you can see it in the variance of the signal. So this is how I know that I have a squeezed light, and also I can lock on it and I can see that it's stable. So this is how you can generate the squeezed light. These are the results that we have for our wavelength, which is rubidium-795, and the degree of squeezing we are getting is 2 dB. But LIGO people, they really, really needed a lot of improvement, and they have a very good squeezers. They work with different wavelengths, and yeah. So what they wanted to do, they wanted to improve their shot noise. Why shot noise? Because that's what they can squeeze. They have many sort of noises, but if you squeeze the shot noise, if you squeeze the noise that comes from light, you can only improve your shot noise dominated region, right? It will not really help here when they are dominated by another kind of quantum noises. So it's important to know in your system what are you limited by, to know what you should squeeze or to where to implement the quantum enhancement so that you can really benefit from that. Okay, and so what they did, they started working on it. They started working on squeezing the light for the LIGO. They started to building squeezers also in the labs to test and to let know. And then they started publishing first results. And here, what you can see is the work that is done by Roman Schnabel and Hans Bacher, that they managed to reduce the shot noise in their experiment that was done for a LIGO collaboration. And you don't see an improvement here because this is not the region that was dominated by the shot noise, but you can clearly see an improvement here. This is one. Then they proceeded more. There were more people working on that. And then they applied this squeezed light to LIGO. And this is effectively what make it possible to detect the gravitational wave detectors, because once they improved the detection with the squeeze light, they saw the gravitational waves. And now the question is, they managed to nicely reduce the noise in their interferometer, and can we do the same in the magnetometer, right? So this is our sensitivity, and the question is, can we improve our detection? And the very fast answer will be given to the magnetometer I showed you before. So this is a very short recap. What we have is this Bell-Bloom magnetometer. We have this magnetic field that is orthogonal to the probing direction. We detect this time domain signal, we demodulate this signal, and we get the noise, the polarization noise. So now the question is, what is the noise here? And can we improve it? So I will make a longer explanation for the multi-parameter system that I will introduce in a while, but just to show you that it did work, I will show you the results for this single parameter magnetometer that I showed you in the previous lecture. So this is the sensitivity of the magnetometer we measured with the coherent light, and this is the sensitivity of the magnetometer that we measured with the squeezed light. And you see that it somehow looks very similar to the LIGO results. So there is a region where we didn't improve, and I will tell you why during this talk when we will try to infer what kind of quantum noises we have in this system. And you can see that there is a region in which we benefited for using the squeezed light. And then, because as we spoke before, in this kind of hot vapor cell experiments and in general in sensors, we are trying always to choose the best parameters to have the good sensitivity, for example, right? So I can put a squeezed light, but maybe my number density was not optimal, and would I benefit from squeezing there? So it's important to check that. So then Hara published another paper when she showed that she benefits from squeezing in the number density optimal scenario. So she measured the response of her magnetometer at different temperatures, at different number densities, and she showed that in the temperature optimal scenario, so when she had the most sensitive magnetometer, she was also benefiting from squeezing.
What's squeezed again here? It's a probe light.
So it's the probe light, yes. And yes, so what we detect, I will tell more now, okay? Sorry, maybe the order was not best. Okay, but how I would like to explain that we really benefit from squeezing and how we benefit from squeezing is on the a little bit modified magnetometer. So this is what you actually saw before, just we now tilt the DC field. Now it will be 45 degrees with respect to the probe and pump, and we add a small RF field. We do it because this creates us a multi-parameter sensor. Before, we were only able to detect the magnetic field, the bias magnetic field amplitude. Now we added RF field, and with this kind of sensor, we will be able to detect two parameters, the RF field amplitude and the DC field. And how it works. So what happens, what is the spin dynamics in these systems? Again, we polarize the atoms with this Bell bloom. We do the spin readout along this direction, and we pump them once per cycle. And then the spin precesses around the magnetic field that is now tilted. So this looks exactly like with the Bell bloom, just the geometry changed a bit. But for us, what is interesting is what it really gives us. What do we get from that tilt? Again, we have this raw signal in the time domain, we demodulate. And when we demodulate, we get two quadratures. Before, one quadrature, this one, was telling us what is the change in the DC field. And now we find out that when we demodulate this magnetometer that also have an RF field on top, we start seeing the response in the second quadrature to the RF field. So now, from the phase and the amplitude of this signal, we can infer what is the RF field and what is the DC field. And this is nice, because this is a hot vapor cell experiment that is really a multi-parameter sensor, and we can do multi-parameter estimation, and this is interesting for many people who try to do this multi-parameter quantum estimation. So it's a very good test bed now to do, first of all, this quantum noise studies, and to use it as a multi-parameter sensor. And what these two graphs proves,
Sorry, I mean, like, you apply this RF field, and this is the quadrature also demodulated at the frequency of the pumping of the light.
Yes, so that's a good question. So how it works, we have a generator that drives the pump, that is our driving force, and the same signal is sent to generate the RF field. It's phase synchronized with the pump, and it all should be equal to the Larmor frequency. So we are trying to match those three frequencies to be the same ones and phase synchronized. Yes.
And then, like, the quadrature wouldn't be empty if it is without the RF even, right? That would be a signal as well.
Yes, yes. Then it would be like a Bell bloom, but tilted with a bit worse sensitivity and weaker response. Yes. But if you add an RF, is your question if this would be flat?
Yes, I know.
I have a backup slide.
I mean, you see, like, the spectrum of a harmonic oscillator in both quadratures, right? There's an X component and there's a Y component. Yes. And here on the right side, we see the Y component, or Z1, that's linear, so that you can measure magnetic field. But the X component, which is the in-phase quadrature, would also show the harmonic oscillator, basically the absorptive signal.
Yes. So if you don't have RF,
it suggests that the RF is sort of changing the amplitude of that in a way.
Yes. Sorry. So if there is no RF, you would still have one quadrature would behave like that, right? And the other would behave like that. So in principle, you can use both to infer the DC field. Just this slope is much better to infer. That's why we choose this quadrature, right? Yes. And now when we add RF, we start seeing this strong response here of a given slope in the in-phase quadrature too. And this would not be there if you don't have that RF field. If you have, no, it's still there, it's just, yeah.
I'm wondering whether you're just scaling the amplitude response, so sort of the whole thing by introducing this RF field.
By adding RF field, I'm increasing the amplitude of the signal.
Yeah.
Yes.
Mm-hmm. And that's sort of where the linear relationship comes from.
Yes. You mean this one?
Yeah.
Yes, yes. So this has to be small to have this linear response. Then if you add the RF that will be too strong, you will start messing with your bias field, right? Because then this will start be significant contribution to the total field.
Okay, thank you.
Okay, and to see a bit more intuitively, maybe we will, no, it will be random. Okay, so here we see how the spin behaves if we have the resonant DC field and no RF. No, no, no. I'm sorry. Okay, I think we don't. But basically what is shown here is that changing the RF field will affect the amplitude of the signal, as you said, and changing the DC field will affect the phase of the signal. That's why after the demodulation, one quadrature will tell us about one field, and the other quadrature will tell us about the other field. And this is like a proof that is a multi-parameter sensor. But yeah, so what is important is that with one atomic ensemble in this vapor cell, we can estimate 2 parameters with one measurement. Okay, and the block equation looks exactly like it looked before. So we have a precession, we have a precession in the magnetic field, right? This we ignore for now. We have a relaxation that is happening due to these different collisions that we spoke about in the previous hour. We have the optical pumping, the Bell-Bloom scenario that is building up the polarization, and then it's keeping it at a certain level. And now we add the quantum contribution. So we add this part that is a spin noise. So this is like a stochastic term. This is just a random fluctuations of the spin. We add this here because it's present there. It's called spin projection noise. And then we add this term, and this is the term that comes because of the measurement back action. So what happens? What happens is that because of the probe that we have there, this probe interacts with the atoms. And this creates this measurement back action that looks like a fictitious magnetic field. What it does, it gives us this random rotation around the Z direction, this term, of the light shift term that comes from the presence of the probe, and this will somehow affect our operation because it will be looking for the atoms like the fictitious magnetic field, right? So we have these two source of quantum noises. One comes from the fact that we probe and we have a measurement back action, and the other comes just because we have a random spin fluctuations in the system. And then there is the third part of noise that is because of our detection. So our detection is not just looking at the atoms because we don't see how they process. What we do, we send a light through them and we look at this polarization rotation, right? So there will be a third quantum noise that is because of the light that we use to probe the atoms. And this is the shot noise, the photon shot noise, exactly same source of noise that the LIGO was suffering from, that is coming just because how we probe the atoms. We do the Faraday rotation detection by looking at this S2 Stokes parameter. So this is this difference between the plus 45, minus 45 polarized light on the balance polarimeter. So what we are interested in is the noise in this S2 Stokes parameter. So we have these two contributions for the quantum noise coming from the atoms and coming from the light. And the atomic part is separated into the spin projection noise and measurement back action. Okay, so what we are expecting to see when we look at the noise, at the polarization noise that we measure, so this is what I showed you here, right? That we look, that we look at this polarization noise, what we are expecting to see is we expect to see three kinds of noises: the shot noise and atomic noise, meaning measurement back action and spin projection noise. Okay, so we will have our spectrum, we will see the power spectral density of our detected spectrum, our noise, and we are expecting to see the flat photon shot noise. Why flat? Because this is just white Gaussian noise. It doesn't choose the frequency. And then we will see another source of noise that will have a Lorentzian response, because what is here is a resonance system, right? The response that is coming to my results coming from the atoms is a resonant response, because it's a resonance system. We are driving in this pumping frequency, and what we do with the noise, we accumulate the noise that comes from the atoms, which means even though these sort of noises itself are flat, we accumulate it at the Larmor frequency, so we have this Larmor response over the atomic noise. So what we are expecting to see is basically a Lorentzian that will tell us what sort of photon shot, spin projection noise and measurement back action we have, and flat offset coming from the photon shot noise. Sorry. Okay. Okay. So again, we go back to what we saw an hour ago, and now maybe we will understand a bit more. So what is this? This is a signal after the demodulation, which means when we had this nice spectrum with a huge peak, what we see now is we see this part basically. We see the noise around the Larmor frequency, right? Because this is after the demodulation. And first what we do, we measure this noise for the unpumped atoms. So this is not a polarimeter, we just measure, like, it will not even look like that. It will look like that. We will see some random precession around the Larmor frequency that comes from our atoms, and this is called spin projection noise. So how do we measure it? We just turn off pumping and we just probe the light, and we can infer what is the level of our spin projection noise. And then what I show here is the fitted spectrum, because maybe it will be easier to see because this signal itself is quite noisy. Okay. And then, as I said, we have the offset from the spin photon shot noise, right? So this is, again, the noise after the demodulation. The flat part is telling me what is the photon shot noise in my system. This comes from the light. Then this is unpolarized ensemble. So I see this noise, and this is spin projection noise. So that's how I can see what is the balance between the photon shot noise in my system and the spin projection noise. And then I start pumping my atoms. And when I start pumping my atoms, I start seeing measurement back action. And then this small contribution here will be coming from the measurement back action. Okay. So we measured this, and then we can define two regions. And one region will be dominated by the photon shot noise, the flat one, and one will be dominated by the spin projection noise. This is the one that is around the lower frequencies. And measurement back action, so basically atomic noise. Okay, again, we do this I told you before. Then we add the responsivity. Just now, because we have RF and DC field, we need to measure two responsivities for the RF field and for the DC field. And with that, we can infer the sensitivity. So we have this noise, responsivity, and I get the sensitivity of my multi-parameter sensor. And this is what we showed in our first work with this device. And now we want to try beat the shot noise. There we want to introduce the squeezed light. Okay, so I have my detected spectrum. And if I use now the squeezer, I will squeeze the light. I don't expect to squeeze the noise in my atoms, because this is the noise that is connected to the way I probe, right? So this is the photon shot noise. So we have this ability in the lab. We have the squeezer, the scheme that I showed you before, we have in the lab, and we are able to generate the squeezed light. And I can squeeze the shot noise. So this will be modified by some squeezing parameter. And these are the results that we used for our experiment. So again, you can see here the result from the spectrum analyzer. So this measures the noise. And then I compare the coherent light noise by just not pumping the nonlinear crystal, not creating a squeezed vacuum. I see some level of the noise, and then I switch on the pump, and I start scanning the phase between the local oscillator and between the squeezed vacuum, and I can see how much of squeezing and anti-squeezing I have. And I can get 2 dB of squeezing in our light, and then I can use this for probing. I can lock my laser here, and I can use this for probing. Okay, but now what is important is to see if we pay the price for squeezing that noise. If I squeeze the noise in one polarization, I start anti-squeezing this in another polarization. And what is very sad for us, that those two Stokes parameters, S2 and S3, are bounded by the uncertainty relation. This means that each time we squeeze S2, we anti-squeeze S3. And now let's go back here for a moment. What we have the detection that is happening with the S2 Stokes parameter, right? So this noise I want to squeeze. But then, because of this uncertainty relation, I anti-squeeze S3. And I see that S3 has a contribution to my atomic noise. So what I expect, because of this, is that each time I squeeze my photon shot noise, I will have to pay the price, and I will see the measurement back action in S3 component, I will see the increased noise in the measurement back action because I anti-squeeze S3. So that's why we put here the anti-squeezed parameter. Okay, and now again, these are the results that you already have seen for the coherent light, and now we added the squeezed light. So we squeeze the noise in S2, and what we see is that the whole signal went down, right? These are unpumped atoms, which means no measurement back action yet. I'm just comparing the solid line for the coherent light with the solid line for the squeezed light. They are both for unpolarized ensemble, so I only have shot noise here and shot noise here and spin projection noise here. And I can see it went down.
There are two traces, dark and bright gray. What are they?
You are not supposed to see the bright yet.
Ah, okay. I'm sorry.
This is the full picture. So one of the traces in the background, the lighter one, corresponds to the solid feed. The solid feed was done to that one, and then the dashed feed was done to the darker one. Yeah, sorry about that. I missed it. Okay. One remark is that you can see here a spike. It's a technical spike. I know that one of my devices were doing what was adding noise at this frequency. So for any feed, we removed this spike and we performed the fitting without that. But to show you how the data really looked like, you can see it in the spectrum.
But what's the difference? I mean, the difference is again pumped and unpumped.
Here now.
Yes, in the gray.
Yes.
Gray spaces.
Yes. So we have unpumped atoms. Sorry, just like here, which means that here I don't suffer from measurement back action. I only have spin projection noise, and I only have the shot noise. And I see that I decreased shot noise, right, in all the frequencies because this is white noise. It's present everywhere. But then when I pump the atoms and I start suffering from the measurement back action, I can see the contribution from the measurement back action. I can see that this level actually went up more significantly than in this case. That is because I had some measurement back action from my coherent probe, right, measurement. But then when I squeezed S2, which means that the whole level went down, I anti-squeezed a S3. So now the contribution from the measurement back action is greater, right? Because I anti-squeezed S3, which means I increased this. So this is smaller than this one. But still, in this given circumstances, in this scenario where we had this balance between the shot noise and the spin projection noise, I'm still benefiting in all the frequencies by using the squeezed light. But you can now imagine the scenario that my measurement back action is much bigger because I use, for example, bigger probe power. And then that at some point I will have worse detection at low frequencies because my measurement back action, because of this, or if just I have more anti-squeezing in the system, right? Then I could imagine that it can go above my coherent state. And then you would have to have a trade-off. You will have better detection at higher frequencies with squeezed light, but you will sacrifice the detection at lower frequencies. Okay, and then we also checked that. For the anti-squeezed light. So here you have a question? Yeah.
Why are you interested in the low frequency range when your signal is at the high frequency range?
Again, why?
Why are you interested in the low frequency range when your signal is at the high frequency range?
Sorry, so this is again the signal after the demodulation. So this is all around 30 kilohertz. And why do I care here? So this is not 50 hertz. This is 50 hertz around my Larmor frequency. So this is when my actual detection is happening. Then when we take into account the responsivity, this become this shape, and this is the low frequency range. So what we don't want to get is, if this was our sensitivity before with the coherent light, now when I add the squeezed light, we can get something like this, right? That we will pay the price here, the detection here will be worse, but it will be a bit better here. But for this particular case, it's not the case, because the spin projection noise was much higher than the measurement back action, and the improvement with the shot noise actually was much higher than the measurement back action. So even if we increase the measurement back action here, we still benefited more from decreasing the shot noise. And then we also checked that for the anti-squeezed light, so immediately the whole noise went up because the amount of anti-squeezing we put into the S2 Stokes component was huge. And then we can see that we didn't worsen the low frequency detection because we anti-squeezed S3 in this case. So this is actually this multi-parameter sensor where you can see the interplay between the three kinds of quantum noises: the spin projection noise, measurement back action, and photon shot noise. It's a great test bed to test this interplay between those quantum noises. And as I said, it's a multi-parameter sensor, which means we were mostly interested if this will work for both the DC detection and the RF detection. So yes, we managed to get quantum enhancement in both, and this is a nice result. So we improved the shot noise for both fields, RF and DC. And then what is actually interesting is the sensitivity, right? So we measured the sensitivity in this sensor with squeezed light probing, and we showed that for both RF and the DC readouts, we improved the sensitivity in the shot noise dominated regime by using squeezed light. And one remark is that it also increases your measurement bandwidth. What is measurement bandwidth is the frequency at which your signal drops by 3 dB. That's how we define measurement bandwidth. And by introducing the squeezed light, you also increase the measurement bandwidth. So not only you improve the magnetic sensitivity, but you also increase the bandwidth of the magnetometer. And yes.
Maybe very naive one. Why are always anti-squeezed and squeezed asymmetric?
They are anti-symmetric. That's a good question, because of the performance of our squeezer. Our squeezer is affected by losses in the system, and those losses comes from losses on the optical elements, losses in the atomic vapor, because atomic vapor can, even though we have off-resonant probing, still something can be absorbed by the atoms. And then we have the detector that is detecting this squeezing that has a given quantum efficiency. And all of this sums up, and the losses will make this balanced situation when you should get anti-squeezing and squeezing same, towards getting more anti-squeezing and less squeezing. And because you have more anti-squeezing than you have squeezing, then when you probe with that, you see it in the sensitivity, that you worsen it much more with anti-squeezed light than you improve it with the squeezed light.
Okay, thank you.
And here are the results that were achieved for the single parameter sensor. So the standard Bell bloom that you saw before, this was measured by Hara and published in 2021, when she showed again the polarization noise for the coherent light and for squeezed light. And again, you have an improvement from the squeezed light, and you don't worsen here your sensitivity for the low frequencies. And here the question is why, again, why you don't see here worse performance at lower frequencies if you should suffer from this measurement bug action. And there is a question, if we have this multi-parameter sensor, we definitely saw that we have a measurement bug action. We increased noise when we started using the squeezed light, right? But is there a measurement bug action with a single parameter sensor? So the source of this measurement bug action is, again, this random rotation around the Z direction, this fake magnetic field, right? That would be creating these random fluctuations around the Z direction. And when you look at the geometry, you can see that this affects actually the phase and the amplitude of our signal. But when we have this geometry, we do something that is called measurement bug action evading measurement. So this standard well bloom, when we have a single parameter detection that we heard about an hour ago, this is the scheme in which we have the measurement bug action evasion. So here, the noise that comes from anti-squeezing this S3 is shunted into the unmeasured spin component. It's not affecting our detection along the Z direction. And this scenario is measurement bug action evaded. That's why when you compare here the level for the pumped atoms with the level of the unpumped atoms, you will see that you have absolutely no measurement bug action. They are on the same level. So with this magnetometer, we can either have the multi-parameter sensor, but we will have some measurement bug action there, or we can have a single parameter sensor, but we will be measurement bug action evading. So it's again a nice system to study this kind of quantum noise contributions. And then what is happening in our lab, these are all macroscopic objects. We have a macroscopic cell in the shields, in the big mu metal shields. We have a tabletop squeezer that is actually taking the whole optical table. But the outlook here is that one can go to a miniaturization of the system, because right now people are working on photonic integrated squeezer that would be as small as this, and then we can replace the macroscopic cell with the microfabricated cell. So there are still some studies done. Can we still benefit from the squeezing in the miniaturized version of our OPM? And that's the outlook. So the summary of the second part is that if we have this quantum sensor, what really matters for us is what kind of quantum noise we have there if we want to improve that sensor. So there is a standard quantum limit that arises from the presence of that quantum noises, and those quantum noises are photon shot noise because we detect with the optical probe. Our detection is optical. We have also the atomic noise that comes from the fact that our sensor actually are atoms, and this is spin projection noise and measurement bug action. So when we have our sensor, we want to see what is the contribution from all of those components and how can we mitigate that. For example, we can use the quantum enhancement, and we can operate below the standard quantum limit. We can decrease the photon shot noise by using the squeezed light, but not only, we can also think of using spin squeezed state, and then we would try to improve the detection at the lower frequency where we are dominated by the atomic noise. Yes, with that, I would like to thank you. This is our group. This is Morgan, who is also here online. And if you have questions, please ask.
Yeah, thank you very much for the super nice talk. There's actually plenty of time for questions. And maybe I start with one because I'm very interested in this. Like there you show that your spin projection noise limited in a way. How would you lower that?
So to lower the spin projection noise, you could use spin squeeze states. And then you could try even to merge it with a squeeze light probing. So to use the spin squeeze states, you would try to do some stroboscopic probing, like, for example, Romalis did. And then you could even probe it with a squeezed light. And then you could try to lower the noise in all the regimes.
Sure, but are you doing that?
Are you?
Are you doing that?
Not now.
Okay.
But we have some plans about implementing a spin squeezing. We did implement, in Morgan's group, they did experiments back in the days with cold atoms where they implemented spin squeezed state to improve the sensitivity of their sensor.
Could we ask Morgan how you implement spin squeezing here?
Yeah, so the work that we did on this was mostly in the publications from 2017, and it's again quantum non-demolition measurement, which means it's a non-destructive measurement of the spin, and so it is through measurement, it is projecting the state into something that is squeezed. The right figure that Aleksandra is showing is from one of those publications, and it somehow illustrates the change of the state as you make repeated measurements on it, and it evolves into this special kind of squeezed state, which is called a planar squeezed state. Yeah, at that point, it is more sensitive to, it's less affected by spin projection noise for short measurements. So doing that will allow you to make a more sensitive measurement for a signal which is changing faster than the spin coherence time. And then there's a completely separate set of questions about whether you could use these kinds of techniques to improve measurement of signals which are slower than the spin coherence time. Did that answer your question?
How would you do it? Like, how do you spin squeeze that?
So in principle, this happens automatically just by doing the Faraday rotation measurement as it is precessing. And so the picture here, what's illustrated here is a spin that's doing some kind of free induction decay. The sphere is changing into spheroids or ellipsoids, illustrates the uncertainty. So initially that's a uniform uncertainty for the biggest, roundest spin uncertainty. And then as you get a bit of information, you're reducing the uncertainty in the Z component due to the non-destructive measurement. And so it becomes squeezed in that component. And because it's precessing around, then sometimes that Z component is the radial component. So sometimes you're squeezing the radial component, and sometimes it's the azimuthal component. And so those two components get squeezed just by measuring. And what you would see in practice is a free induction decay signal, which is somehow, which you can interpret with less uncertainty after you've measured for a while than at the beginning. At the beginning, before you first start probing, then you would have a standard quantum limit uncertainty set by the spin projection noise, by the uncertainty of the state. And then after you've probed for a while, you would know more about it. And so you would have less uncertainty about the state. And so when something happens in your free induction decay, say the frequency of the free induction decay changes, you would be able to interpret that with less uncertainty as a change in the magnetic field strength.
Yeah, thanks. Mute him. Okay, I'm sure there are other questions. Oh, didn't even have to walk.
Thanks. So I have a follow-up question on the one I asked earlier about the squeezing. And we had this graph where you squeezed the X direction and it got wider in the P direction. And I'm just wondering, if we weren't yet at the Heisenberg uncertainty limit, why did the P direction have to get wider when the X got narrower?
Why do you add more noise to the unmeasured component?
Yes.
I mean, that comes from the uncertainty relation directly, right? That if you know this very well, this has to get increased.
And how again does it happen that you manage to decrease the area or to decrease both of them?
here with respect to this,
Yeah.
because this is completely before you start the measurement. Morgan, do you want to add?
Yeah, I think the picture here is that if you look at the fourth or the fifth graph, then this is after both X and P have been measured. And that is at the Heisenberg uncertainty limit for the area of the state. And so what you see in the first graph is clearly more than that. There's much more area. That indicates some uncertainty, which is larger than the Heisenberg uncertainty, or an uncertainty product, which is larger than that. So that might be if your state was prepared in some noisy way, or if you simply didn't know what the state was because you haven't gotten any information about it. And so in that situation where your area is larger, then a measurement can reduce the area.
Thanks. No, I think that's okay.
I think the question is a bit why the area reduces in general, right?
Why would a measurement reduce the area?
Because you measured, you decreased here, if I understand correctly, Morgan, tell me if I'm wrong. Here you measured X, right? So you, so you decreased the uncertainty there. And then at some point you measured P. So you decreased the uncertainty in P. But what Morgan said, this is already the Heisenberg limit here. So from now on, you will not be able to decrease it more, and you will have to squeeze in an anti-squeeze it, but not you will have to change the distribution of the noise in X versus P, whatever you measure. But this was just representing a state that is not in the Heisenberg limit. You had much more noise, and then you decreased it as much as you could by measuring X and P, and now this is operating at the Heisenberg limit.
The thing that still confuses me is that the first measurement made X narrower and P wider, and the second measurement just made P narrower, but it didn't make X wider.
Yeah, I think maybe that's my fault.
And I thought because of your explanation,
But this would have happened if this was the Heisenberg limit, right? Yeah, we hear you.
Okay. Should I try?
Yes.
I think the confusion here might be my fault, that I said measure P, and that's not very careful way to describe it. The picture here is that the only measurements that are made of X, but between a measurement of X at one point in time and a measurement of X at another point in time, then the state can rotate. So in going from the first to the second, there's a measurement of X. In going from the second to the third, there's a free precession, or in the case of a harmonic oscillator, simply free oscillation, and that probability distribution rotates. Going from the third to the fourth, there's a second measurement of X. So in that,
it's the uncertainty that oscillated from being uncertainty of X to being an uncertainty of P.
Exactly.
that did actually help. Thank you.
Okay, I'm glad. Sorry for the confusion.
So coming back to that squeeze, I actually have two questions that are probably unrelated. So coming back to that spin squeezing question, I was wondering whether it might be possible to have like a nonlinear, for high densities, nonlinear interactions in your ensemble to get spin squeezing through the collisions or interactions within the gas, or is it maybe requires too much, a much higher concentration than possible? And potentially a different question is whether there's, I mean, that was kind of relating to the miniaturization thing. Is there a fundamental limit to how small you can go? I mean, not just technical problems, but is there something more fundamental in terms of how small you can make these cells or systems?
Bart?
Something's wrong with the microphone, so I think he didn't hear you. Did you hear Nia's question, Morgan?
Those questions were for me.
Well, yeah, they are now.
Okay, so for the first one, to my knowledge, there's no experimental work on spin squeezing in vapors using interactions. It has been a very active topic with ultra cold gases, so with Bose-Einstein condensates. And in fact, it seems like something which is much better suited for ultra cold gases because you have collisional interactions which to some extent you can control, and also which are naturally all to all. So you have a Bose condensate where all of your atoms are in some sense in one big wave function. All of the atoms can interact with all of the other atoms at the same time. Whereas in a vapor, which atoms interact with which other atoms is always going to be somewhat stochastic, because it depends on the collisional physics. And also it's never going to be all of the atoms interacting with all of the atoms. But it's a very interesting question, and I would not rule it out as a possibility. And then is there a limit to how small you can make a cell? I don't think there are any fabrication limits, because this is based on silicon. The MEM cells are based on silicon microlithography, and we know that can generate nanometer size structures if you want to. So there's no limit there in the size of the cell that can be produced. But there would be a limit in the size of the cell you would want to produce. When you make the cell smaller, then you're bringing the walls closer. And so all effects that are related to wall collisions get worse. And which is to say that your sensitivity or your coherence time is going to get worse. There is nonetheless an interesting regime, which is between, say, 10 microns and 1 millimeter, where it's not clear whether nitrogen vacancy centers or whether atomic vapors would do a better job with that regime. And so it's an interesting thing to ask: can you push to cells that are smaller than a millimeter in dimension, or that have vapor volumes that are smaller than a cubic millimeter?
Thanks. More questions over there?
Yeah, thanks for the nice talks. I have a question which maybe fits better to the first talk. You mentioned that there is always a trade-off between the temperatures or the number of atoms which you have, which contribute to the signal, and the coherence time or the relaxation time, which you want to be as high as possible. So I wondered if there is some efforts going on to improve this by using, for example, an optical cavity, so you could effectively increase the number of atoms which contribute to the signal, but can have in the cell itself a smaller number of atoms, which means a higher coherence time.
So there are definitely the research that are going towards cavity enhanced OPMs. So the bacteria measurements I mentioned, this is exactly the MEM cell that is placed inside between the two mirrors, and they are doing the cavity enhanced readout.
Okay.
Readout there. So yeah, people are using that. People are using also like multipass cells for that reason, so that the light goes and it goes through a cell multiple times to pass through the atoms, and then it leaves the cell. So yeah, definitely there are research going towards that direction.
Yeah, thank you.
For the kinds of measurements you do, are you limited in how long you can integrate across? And if so, do you find that there's a significant trade-off in only being able to measure during your squeeze state versus the noise decrease?
For the squeezed state measurements, is there a time to which I can measure? You mean the length of the measurement?
So the kind of measurements that you do you find you need to integrate over long periods of time to actually get that? And do you find that there's a trade-off in only being able to measure during your squeezed state? Because that duty cycle seemed pretty rough.
So what is happening, what you see here is actually a noise that is averaged over taking 100 samples, and each sample was 1 second long. So here what I have is a data acquisition system, right? So first I want to have a good sampling rate to have a big bandwidth on my data acquisition card. This allows me to gather, this is a technical limitation that allows me to gather some length of the measurement, okay? And 1 second for us is enough. And then when it comes to using a squeezer and time constraints is actually the stability of my noise log, right? So this is a system that depends on many different, it can fail in many ways. You can unlock the blue, you can unlock the squeezed vacuum, you can unlock anything. So you can lose this squeezing after some time, and you want to be sure that you are always measured when you are really having a squeezed light and when you have anti-squeezed light and coherent light. So what we do, we rather limit this time to a short cycles, and then we measure with the coherent light like few tens of samples, then with the coherent, then with the squeezed, and with the coherent, so that I'm also kind of immune to the drifts that can be happening. Because the squeezed, the noise floor, how I know that I have a squeezed light is I compare it with the coherent light noise, right? But then you can imagine that what if my power drifted, right? If my power drifts of my light, the short noise of the coherent light just goes down, right? So at some point it can look like a squeezed light, but it's just a drift. So to be sure that I'm squeezing and having a coherent light, I divide my measurement times into a few tens of cycle, but separated in time by different measurements. And then I average all of them to know that this is not like a difference because of some drifts or some technical issues in the lab, but due to squeezing and not squeezing of my coherent time. But yeah, this is a lot of averaging.
For the talk, there was a slide where you showed that the noise was lower when it's unpumped versus when it's pumped. Yeah, I was wondering, how come a reduction in the
for the unpumped, why this level is lower?
Or measurement back action, because I typically associate measurement back action with like any circular component in the probe light rather than the pump.
So are you asking about this difference?
Yeah, like why is this difference arising from unpumped versus pumped atoms?
Because I see the contribution from the measurement back action only when I have the polarized ensemble. And what is measured with the solid line, it's a noise of my magnetometer that is for the unpumped ensemble. So this is just the spin projection noise of, it's not a magnetometer yet, it's a noise meter, I would say. I only can measure the random fluctuations of the spin. They are not pumped. They are not processing, they are not pumped in this cycle that I showed. So this is just a random spin fluctuation. So this is only the noise that comes from these random fluctuations. There is no measurement back action there yet. That's why it's lower. And then when I add pumping and I have a magnetometer and I can, I'm driving them with the pump, and then this is resonant with the Larmor frequency and so on, then I start seeing the contribution from the measurement back action. So they start being affected, because this is like the measurement back action is like the fictitious magnetic field. So then later on, if I have this resonant response, right, I'm affected if it's not resonant anymore. And then this is just like a noise, but it's a noise on my magnetic field. it's a noise on my magnetic field. It affects my magnetic field. So then I start seeing this in this system that gives me the resonant response, and this is only when I pump the atoms, when I have polarized atoms. That's why I see that noise only for the polarized ensemble, because here I'm sensitive to that.
My question is regarding the time during pumping. Could you use I'm not exactly sure if it has been done before or if you guys have done this before, but could some sort of parametric up conversion or down conversion during the pumping time, where you maybe generate an entangled state and then use some sort of this kind of probing, would that then improve better than just having a regular pumping?
You mean pumping the atoms?
Yeah,
Pumping the atoms in the magnetometer?
Yeah, in let's say parametrically, let's say some kind of parametric down conversion process using multiphoton or parametric down conversion process during pumping, where we generate an entangled state, spin state in the ensemble itself. Is this some kind? Is this possible?
Thought of it, Morgan?
I think I still did not understand whether you're asking about generating a non-classical state of light or using it to generate a non-classical state of the spins.
Of the spins.
Of the spin, Morgan?
Yeah, I think, well, if you ask whether in principle that could work, then yes, I think you would be able to do something in the pumping that would generate a non-classical state of the pump light and then use that to make a non-classical state of the atoms. At the same time, I think that is unlikely to be an efficient method, in the sense that it's going to be difficult to transfer any quantum advantage from the pump light to the atoms, because somehow that process is very noisy, that in addition to absorbing the pump light, which could be almost deterministic, you also need lots of emission processes in the optical pumping, and those would add noise to it. But yeah, I think in principle it would be possible to use non-classical light to pump, and by pumping generate a non-classical state of the atoms.
Oh, there's another question. Maybe last question?
Hi, thank you for the lecture. I'm trying to understand what sort of equipment or instruments you would use to actually read out, whether it would be counters or some sort of imaging, or what is it exactly?
So what we have? We have the balance detector, and we do care that this balance detector has a low noise, because what is very important for us is to be limited by the quantum noise, not by the technical noise. So we care about the noise of our detector to be lower than the short noise in our system. And then the signal from the balance detector goes to the data acquisition card. And that's how we acquire actually that in the experiment. And again, here it is important that the noise of the data acquisition card is low. But on the way, we will use different instruments. Sometimes we will connect this balance detector to a spectrum analyzer to see the noise. And actually, when I'm measuring with the squeezed light, I prefer now to divide the signal into two, and one part goes to the data acquisition card, the other part goes to the spectrum analyzer, so that I'm sure all the time that I have this squeezing or not. So when it comes to the detection, yes, we use this balance detector that is low noise. We use the data acquisition card, and that's it.